Okay, so in the previous lecture we were discussing about fields, so let's continue that discussion. So a quick recall what we discussed in the previous lecture. So we discussed what a field extension is, and then we discussed that what is meant by an algebraic element, what is meant by a transcendental elements, and then we talked about a specific case of these elements which we termed as algebraic numbers and transcendental numbers. So algebraic and transcendental numbers are specifically complex numbers which are algebraic over C and respectively transcendental over C. Moreover, we discussed the motivation behind studying such fields, or one such motivation at this point for studying fields. Then we discussed a bit about what basically an extension looks like, or specifically we talked about what is the concept of a polynomial, what is meant by a root of a polynomial, how can we construct a polynomial given a certain root in an extension field. But the most important thing which we talked about in the previous lecture was the evaluation map, or the substitution map, right? So let me just recall. So recall, let alpha be an element of K where K is a field extension over F. So we defined the evaluation map, which was given by f of alpha from ft to k, such that f of alpha acting on some polynomial pt was just p of alpha, right? This was the basic definition. Now we also defined the, or rather discuss the case about the kernel of the substitution or the evaluation map. So there were only two possibilities, that either it is generated by some non-zero polynomial pt where pt is not identically zero polynomial, or it is just the zero ideal, right? So the reason behind this was simply that ft is a principal ideal domain and this kernel forms an ideal of ft. So this was the basic case. And we also discussed this field which is called the fraction field. So it was the fraction field of fx. Okay, so it was the collection of all rational polynomials, over Q, right? Now, so this is basically a what the back fractional field is basically the what we called also the quotient field of a given ring, so precisely a given integral domain. Now I will bring a detailed lecture on quotient fields in my channel in my playlist on ring theory, but you can just consider, for example, the quotient field to be suppose Q is the quotient field of Z, and if you just recall what Q basically is, so it is the collection of sets of the form P by Q such that P and Q are the elements of Z and identically Q is non-zero. So in very simple terms, if I have an integral domain, say R, and what I do is basically I collect elements from R, say A and B, where B is specifically non-zero, and I consider the elements of the form AB inverse, and I consider these sort of elements in some way, and this I name as, let's say, Q only, simple Q. Let's not use the notation for rationals, let's just use a simple Q, and this in some sort acts as a field over R, let just simply R, and this is some sort of called a quotient field. So it is just actually constructing a field using the elements of the underlying integral domain. We will have a detailed discussion on this, but in very simple observations, you can think fx to be the field analog of fx, of f square bracket x. Clear? Okay. Now let me continue. So what we essentially try or intend to do in this lecture is that I want to, so more or less the idea is to adjoin roots to a field. Okay, what I am trying to do is that, for example, let me just start with an example. For example, let kb is equals to r and fb is equals to q, and consider root 2 as an element of R as a field extension over Q. Clear? Now we know that this we have also seen in the previous lecture as well, that if I consider the evaluation map at root 2, then I eventually reach the irreducible of Q of root 2 to be x square minus 2, right? So let me just prove this first. Let me prove this as a statement, then I will continue. So claim the minimal polynomial or the term I used in the previous lecture, the irreducible of root 2 over Q is x square by 2, x square minus 2. So I actually mean the, so what it basically is, let me just give a recall how we used to define the irreducible polynomials. So what we used to do is that, let me go back to where I recalled the so this is called the irreducible polynomial. This pt is called the irreducible polynomial of this element alpha. So provided a substitution map with respect to some element taken from the field extension, and then I take into consideration the kernel. If that element is algebraic over the underlying field, then the kernel will be a non-zero ideal, and since the kernel is an ideal of a PID, so therefore it is generated by some monic irreducible polynomial, and that very monic irreducible polynomial is what we call the irreducible or the minimal polynomial of the element alpha. So this is what we intend to prove in this case. What we can specifically do is that we can show, so we show that the that any polynomial ft belonging to qt such that f of root 2 is 0 is divisible by x square minus 2. This is what we actually do, but actually this is quite easy to show, because see we so q is a field. This implies that qt is an Euclidean domain. So qt is an Euclidean domain, which in fact says that qt is a unique factorization domain, and in fact a PID as well. So therefore we can talk about division inside this integral domain. So so we choose a polynomial ft. So let ft belong to qt such that f of root 2 is 0. But then since x square of so I want to actually divide f by x square minus 2. So on dividing f by x square minus 2, we have, so this just follows from the Euclid's division algorithm, that In fact, I don't need to consider it as a UFD. It was a this was not needed. I actually need it to be an Euclidean domain in order to talk about a division. So whatever. So in dividing f by x square minus 2, we have ft to be written as some polynomial qt times x square minus 2 plus rt. And if you recall, the Euclidean norm or the field norm defined on the integral domain of polynomials over fields is basically the degree of the polynomial, right? Such that rt is 0 or degree of rt is less than the degree of, so in this case it is less than the degree of x square minus 2, because we are considering x square minus 2 to be the divisor, so I can just use 2 here, right? But we know that f of root 2 is 0, and if I put just f of root 2 here, I will get here r root 2, because this part will eventually become 0, but then f of root 2 is also assumed to be 0, therefore r of root 2 is 0. But degree of r is less than 2, suppose it is non-zero, suppose r is not identically 0, then r is a 1 degree polynomial. This implies that r of t must be of the form t minus root 2, but this is no more a polynomial over qt, as root 2 is not an element of q. Therefore, you can talk about this being a contradiction, or you can just not suppose this, and you can and from this you can claim that r cannot be a degree 1 polynomial as well. So r needs to be a degree 0 polynomial, but then since r of root 2 must be 0, and if it is a degree 0 polynomial, so it's eventually a constant polynomial, so you can talk about in that way, right? So but the conclusion in either cases is that therefore the r is identically 0, which means that the polynomial x square minus 2 divides ft, right? Clear. Therefore the kernel of the evaluation map, so I was using f, right? Kernel of the evaluation map f induced by root 2 is generated by the element x square minus 2, right? Okay, so this is by far good. What we want to do is that, so as I just said, I want to adjoin roots to q. And what do I mean by that? Now, root 2 is algebraic over q, right? But root 2 is not an element of q, right? Clear? So what I want to do is that I want to adjoin root 2 to q, and hence form the simplest such structure. That is, I want to form a field, simplest such field, I should use the term, because we are talking about fields here precisely, and fields are the best behaving rings. So simplest such fields. So what I am trying to do is that basically I am trying to construct a field such that, so just write it down. So I want to construct a field, say L, such that, now we are all talking about a field, so within a field extension, right, such that L is a subfield of K, or here we are talking about Q, right? So let me not use the terms in this case. I want to construct a field, let's say Q tilde, such that Q tilde contains Q and the element root 2. You are getting my point? And in a similar way, I can construct such a field, if I am able to do it in this case, I can construct such a field for any root alpha where alpha or root alpha is irrational, or in fact I can also say something more, that when root alpha is not in Q, whatever in this case. And I actually want to do this in a general notion, so I actually want to do this on a general case. So what I'm trying to do is that, or in this case, let me just use the notation in this case, first define a notation in this case, and then we will move on to the general case. So we do that, or we do this rather, we do this by constructing a field using the substitution map, using the substitution map denoted as q round bracket root. Clear? So by our intention, q round bracket root 2 is the smallest subfield for a given extension of q such that it contains both q and root 2. So this leads us to the following definition. Let alpha be an element of k and k over f be a field extension. We define the field f round bracket alpha to be the smallest subfield of k containing both f and alpha. Clear? Got this? Now what we want to do is that we want to give a structure to f of alpha, because without a proper structure to f of alpha, because f of alpha is nothing but a collection of elements, which is quite obvious from its definition. It's just a collection of elements. It's an abstract collection of elements. So if you do not know the structure of the elements in f of alpha, then it is of no use, right? However important the definition carries, if you do not know the structure, if you do not know the elements in f of alpha, f of round bracket alpha, then it's technically of no use of studying it. So our intention is to give a structure to f of alpha. So we want to give, or rather study, the structure of f of alpha. Okay, and how do we do this? So let me just start with it. Now when we were studying the example, we started with an element which is algebraic over q. So in this case we will also do the same. So let alpha belong to k, a subfield of f, be algebraic over f. Clear? Now, so I am just not writing the steps anymore, which I did in the previous lecture in case of substitution maps. Or let me do it. Then consider the substitution map f of alpha from ft to k such that f of alpha of a polynomial gt is given as g of alpha. What we do is that consider the image set of this polynomial f of alpha to be just f square bracket alpha. And so what is the logic behind such a notation? See, if so g is an element of ft, right? So therefore I can write gt as, say, a naught plus a1x and so on till a n x to the power n, let's say. But then what is f alpha of gt? So it's just g of alpha, which is just a naught plus a1 alpha and so on till a n alpha to the power n, or it is just gt where I just put alpha in place of t. So that is some sort of a logic for using this notation f of square bracket alpha, because we know that f of t denotes the collection of all polynomials in t, right? And in fact these are the elements which constitute the whole set of the image of f of alpha. So we consider this. Now what we do is that now this is a well defined homomorphism. This is quite easy to justify. This is a well defined ring homomorphism. Clear? Because if you multiply two elements, then you will eventually get their respective images with respect to alpha and a product of them as well. So this is a well defined ring homomorphism. There is nothing complicated there. Whatever. So I can actually use the first isomorphism theorem in this case, right? So by first isomorphism theorem, what I have is that ft. Now since we are talking about alpha being algebraic, so there is a respective irreducible to alpha or a minimal polynomial to alpha, which I denote as pt, and this should be isomorphic to the image of f of alpha, which we have considered as f square bracket alpha. And I already know the structure of f square bracket alpha, so let me just precisely write it down here once for clarity. So f square bracket alpha is basically the collection of elements of the form a0 plus a1 alpha and so on till an alpha to the power n, such that each ai comes from f. Clear? Okay. Yeah, so let's continue. Now observe that provided that f of alpha, every element of f of alpha has this form, you can easily justify that f of alpha is in fact contained in f round bracket alpha by its definition. The reason is very simple. See, if I choose out an element from f square bracket alpha, if I choose out any element, suppose I choose out an element of this form of f square bracket alpha, then this element will be obviously in f round bracket alpha, because f round bracket alpha is a field and it contains both f and alpha. So it will contain any linear combination which includes the elements of f and elements alpha in this form. So eventually this will be an element of f of alpha as well, right? Clear? So but we know that f is sitting inside f of alpha, because it does so in case of f of t for an identifier t. And if I consider the polynomial p of x is equals to x, then I will see that p of alpha is equals to alpha. This is also an element of f of alpha, f of square bracket alpha. Therefore the field f and the element alpha both are inside f square bracket alpha, and by definition f round bracket alpha is the smallest field containing the field f and the element alpha. Therefore this implies f round bracket alpha must also be contained in f square bracket alpha, in fact, which means that f square bracket alpha is equal to f round bracket alpha, and hence we have given a well defined structure to f round bracket alpha, that is, it is just the collection of elements of this form. So it is just the collection of elements which are polynomials over f, with the identifier being set to the element alpha, being fixed to the element alpha. Clear? And it can be equivalently identified as equivalently f of alpha is just isomorphic to f of t modulo pt, right, where pt is the irreducible of alpha over f. Clear? And in this case we use the term that this f of alpha is called the extension generated, or we also use the term induced by alpha, which is in K. Thus given this definition, therefore what should be Q root 2 by definition? So it should be collection of elements of the form a0 plus a1 root 2 plus a2 root 2 squared plus a3 root 2 cubed and so on, right, till let us say some an root 2 to the power n, such that each ai comes from Q. Now there is an important thing to observe here, which is that, see, this element, it is just 2 times a2, but then I can actually adjoin a0 and 2 times a2, and it will eventually be an element of Q. Similarly, if I choose any even power, then that can be connected with the constant terms or the coefficient terms, the terms which do not have the root 2 together. So next I will have here a4, and I will have root 2 to the power 4, which will eventually be 4, right? 4a4, and this thing will continue. So this thing I can collectively call as a, and all the other terms will contain a root 2 term, because see, here I have a1 root 2, so here I have a1 root 2, then I have a3 root 2 cube, so here I have 2a3 root 2, right? So every odd power term will contain root 2 after evaluating this to the immediate previous. So if I have root 2 to the power say 2k plus 1, then I can write this as root 2 to the power 2k times root 2, and this will get eventually evaluated to an integer and eventually into Q. So I can actually take root 2 common outside from here. So just I can write this as a1 plus 2a3, and I take the collection of all these coefficients which comprise of the odd power, and it continues, and I can eventually write root 2 here, and I can consider this to be completely as an element of Q under closure, because Q is a field, as B. Thus we can observe that Q root 2 is just the collection A plus B root 2, such that A and B comes from Q. Got it? Now there is an important thing to notice here, which we will be considering in the next lecture, that is, see, if I consider a field extension K over F, then I can consider K as an F vector space, K as an F vector space, right? So if I consider the same in this case, see, Q root 2 is a field which contains Q, right? So I can consider Q, therefore Q root 2 can be considered as a Q vector space. And now what I can do is that I know root 2 is an element of Q root 2 by definition. I can consider this set 1 root 2, and you can easily observe that this is a linearly independent set. Just go by as we do in case of vector spaces. This will eventually be a linearly independent set. Moreover, this is a basis. If you observe, this is a basis of Q root 2 over Q, because every element in Q root 2 is just a linear combination of these elements where the coefficients are coming from Q. Therefore I can say that the dimension of Q root 2 over Q is 2, and if you carefully observe, this is nothing but the degree of the irreducible of the element by which this extension is induced, that is root 2 over Q, and this dimension will be referred to as the degree of extension. Degree of extension induced by root 2. So this will be covered in details in the next lecture. So I am just giving the hint to it. In general, if I consider the extension induced by alpha, then the dimension of f of alpha over f, that is as a f vector space, is basically the degree of extension of it is basically degree of extension of f of alpha over f, and this will be eventually being the degree of the irreducible of alpha over f. And keep in mind, all these discussions are being done provided alpha is algebraic over K. I am not discussing any of these concepts provided alpha is transcendental over K. I am discussing these things provided alpha is algebraic over K. Clear? So what happens if alpha is algebraic? What happens if alpha is transcendental over K? Let us talk about that in this case. Uh, should I have should I discuss anything more? Let me just think of it once. I guess I don't need anything more at this point. I can directly talk about. Yeah, let's go to the case when alpha is transcendental, but that's quite an easy observation. So let me go by the same steps as previous. Let alpha be an element of K, K be a field extension over F. Then so suppose alpha is transcendental. Suppose alpha is transcendental over F. Clear? But then we know that considering the evaluation map, where do I consider this evaluation map? I consider the evaluation map at alpha. So the obvious notation, f of alpha, we have kernel of f of alpha to be 0, right? How is it f of alpha is getting mapped? F of alpha is mapping f of t to k, such that f of alpha for any gt will be eventually g of alpha. But I know that alpha is transcendental over K, so the kernel of this map should be the 0 ideal, and which eventually speaks of the fact that Fx is isomorphic to f of alpha square bracket alpha, where f square bracket alpha is again the image set of f alpha. And this again follows from the first isomorphism theorem. But the point here is that Fx is an integral domain. So this is an integral domain isomorphism. But I can immediately talk about a field isomorphism in this case, or of isomorphism in terms of fields, whenever by taking the quotient fields of each of them. By taking the quotient fields of each of them. Therefore, what I can say is that the fraction field or the quotient field of fx, that is f square bracket x, so round bracket x, is isomorphic to f alpha. Clear? So in the case of transcendentals, we have this case, and this is you can obviously observe that this is actually if and only if condition, because if f of alpha is isomorphic to f round bracket x, then eventually that means that alpha cannot be algebraic over f, because we cannot get a polynomial over fx such that f of alpha is 0. Clear? Got it? Now I should discuss some things before moving on to the next lecture, which I'll probably provide by the next class. So since I have given a brief introduction to what a degree of extension is, I should actually give some tools which will make it easier for us to discuss this in the next lecture. So let me just frame it as a proposition. If alpha belongs to K as a subfield of F is a field extension, with the irreducible of alpha over F being Pt, where Pt is explicitly given as a naught plus a1t and so on and so forth till say a n t to the power n, then or you can just think of the fact that degree of Pt is n, then the collection 1 alpha square and so on till alpha to the power n minus 1 is a basis for the field f of alpha for the f vector space, f of alpha. Clear? Got it? So this is actually what we want to prove, and actually proving this is actually quite simple, because observe that. So we have already know the structure of f of alpha. So what is the structure of f of alpha? The structure of f of alpha is basically the collection of elements of the form a0 plus a1 alpha plus a2 alpha square, and so on and so forth till an alpha to the power n, such that n is in such that n is in ai, each ai is in q, f, right? Yeah, correct. Okay, I have this in hand, right? I should be more explicitly doing this in this way. Okay, let me not start with this. Okay, let's do it in this way. So I want to claim that f of alpha, every element of f of alpha can be expressed as a linear combination of elements 1 alpha alpha square till alpha to the power n minus 1. No, I actually think I can do that. Okay, so let me do it in this way. Let f of alpha be an element of f round bracket alpha. Then precisely f of alpha is some sort of this form, right? a0 plus a1 alpha and so on till say an alpha to the power n. But I can use division on f of alpha, right? By dividing f of alpha by p of alpha, or rather I can use the term p of alpha, we get f of alpha to be some g of alpha times p of alpha plus r of alpha. Let me not go by such an abuse of notation. Consider pt, ft, okay, where t is an identifier. I guess now people can understand what I am trying to say. So consider ft. Clear? Divide ft by pt to get, so I will get eventually ft to be some qt times pt plus rt, where rt is obviously the remainder of this division, and eventually it obeys whatever properties it must obey in terms of division. I am not writing that anymore. But then observe, if I put alpha in place of t, so this implies that f of alpha is equals to q of alpha times p of alpha plus r of alpha. But then p of alpha is 0, because by definition p is given to be the irreducible of alpha over f. So this is just r of alpha, right? But now degree of r is less than degree of p, so it can be at most having this r considered as a polynomial can have degree at most n minus 1, right? And f of alpha is an element of f round bracket alpha. This implies that f of alpha is some sort of this form, say b0 plus b1 alpha and so on and so forth till b to the power n minus 1 alpha to the power n minus 1, where bi's can be, or each bi coming from f, or let me just keep it like this, right? And this element f of alpha is coming from f round bracket alpha, which eventually mean that these elements 1 alpha till alpha to the power n minus 1 spans f of alpha, right? Because any element from f round bracket alpha is a linear combination of these elements 1, see this is 1, right? So it is a linear combination of these elements 1 alpha till alpha to the power n minus 1, where these bi is coming from f, so it spans f alpha. So what is the reason behind that? Let me just write it down as, for each f of alpha coming from f round bracket alpha, it is a f linear combination. That is what precisely it means. It is a f linear combination. It is a f linear combination of the elements 1 alpha to alpha to the power n minus 1. I guess now you got the point. Clear? Got it? Okay. So we are just left to show that this set is in fact linearly independent. Now consider a linear combination of these elements. Say, so suppose consider any linear combination, say a0 plus a1 alpha and so on till an alpha to the power n minus 1 to be equal to 0. Okay. Now observe that let f of t be this polynomial a0 plus a1t plus ant to the power n minus 1, which is obviously an element coming from ft, but then f of alpha is 0, but degree of f is less than degree of p, and degree of p is given to be the irreducible of alpha over f. Therefore any polynomial, so let me just go by one more step. So this implies p divides f, right, but degree of f is less than degree of p, therefore a contradiction. Thus this ft must be identically 0, or all ai's must be equal to 0. So what then this basically means that this set is linearly independent as well. 1 alpha to the power n minus 1 is linearly independent, and therefore so this forms a basis. Indeed, the dimension of f alpha over f equals the degree of the irreducible of alpha over f, because the degree is n and we have exactly n vectors in the basis. I guess this part is clear. Okay, so one remark which I should have given, have I given this, that if I choose an element out from the field inside a field extension, then that is evidently algebraic. That is evidently algebraic if the element is inside the field itself. Have I given this? Okay, let me not go back this much. Let me just add it as a remark. I don't remember whether I have given it or not. So remark, let alpha be an element of k over f. This is a field extension. Then alpha belong to f is always algebraic over f as the polynomial x minus alpha belong to ft, sorry, fx is the required irreducible of alpha over f. Now I guess in some places I have denoted the polynomial ring to be ft, and then I chose the polynomial out of it in terms of x, but that's just a problem of habit of expressing polynomials in terms of x, but I guess conceptually it was all correct. So that's enough for this lecture. In the next lecture we will be talking about isomorphic field extensions, and degree of extensions, and then we will be moving on to the concepts of algebraic extensions. Okay, so yeah, that's enough for today. Meet you guys in the next lecture.